Hello everyone. Can I have your attention please?
Good morning.
Good morning. Good morning. Good morning. So today we will have a little bit of experimentation with some stuff. Basically the idea is to check what we have seen so far and whether it makes sense. So far we did a lot of mathematical analysis. Now it's the time to see whether those mathematical analysis actually holds true in real life. So we talked about electric field, we talked about voltage in the class. And from our discussion yesterday, we said that the voltage V has a relation with electric field like the following. Voltage with electric field if you integrate the entire electric field over a distance. And we know that the electric field for a charge Q at a distance r is kQ by r squared. If you integrate electric field over a distance r, we will get the voltage is kQ over r. That means if you have a charge, positive charge, and you bring something, bring a test charge from a very far distance to a closer distance, which is r distance away from the Q charge, then the corresponding voltage is the same everywhere on the circumference of the circle that you can draw, with the center at the position of Q. And everywhere on the circumference you will have the same voltage equal to kQ by r. Right? So we also know that if you increase the distance, the electric field is going to reduce. Right? The electric field is going to reduce with proportion of 1 over r squared. And simultaneously, the voltage is also going to reduce in proportion to 1 over r. Right? So, what we have here is, let me see if I can put it on the screen. Like that luck is not in favor of us today. So we just rely on our eyes. Alright, so let us just use our black eye. I hope that people can see from your position. So what we have here is called a bandy graph. highly tough generator. The way it works is the following: that if you take this array, you see that it has a piece of rubber, okay, and that piece of rubber is rotated by a machine. Electrically, it keeps getting rotated. So when it keeps getting rotated, it gets friction with other stuff, and because of the friction between two materials, it creates some extra charges. Okay? Now, let's say that we are getting some positive charges. So on those positive charges will be collected by this metal, and if I place another metal on top of it, this guy is also going to get the same amount of charge. Now, we know that the atom is neutral. So if we are going to get a positive charge here, then of course there will be some negative charges stored on the other side. So those negative charge will propel down to all the way to the bottom. On the bottom we also have another metal. That's a ground.
Sorry, what is the two, I guess, points of where the friction is? What is the...
So one is the middle,
okay,
and the other is the rubber. So
okay.
if you rub these two stuffs, you are going to get some accumulation of charges. Those charges will be positive or negative. What exactly is the sign of the charges, that we will see. So let me connect this guy.
Yeah. I don't think the tables have to be plugged in.
Oh.
Will it reach?
So what do we do?
There's an outlet over here. I don't know if it'll reach.
There's one behind you. There's one behind you.
Behind you? Oh, yeah, right behind you.
Yeah.
Since you're late, you have to follow through.
Yeah, I'm sorry, Charlotte. Traffic.
Oh, sure. That's you.
Okay, thank you. All right. So it looks like it's a dangerous situation. I can trip over any time. But anyway, we're doing science here, and we can sacrifice all that for science. And believe me, this guy that we're going to see is going to generate some significant amount of voltage. So one more time, how much voltage is there on those power sockets? 110 or 20. So the battery that we typically use, like the small batteries, they have a voltage of like 1.5 volts. It can go up to 9 volts, something like that. So these guys, it's already having some practice. So this guy is supposed to generate very high voltage. Okay? And we are going to measure how much voltage will be there. So in order to measure voltage, we are going to utilize a voltmeter. So what we're going to do is that we will connect the positive and negative terminal of this voltmeter with the ground and these metal guy. So as I say that because of the friction, this metal guy is going to get some charges and the ground is going to get the opposite charge. So if I connect them and begin rotating the machine, I should be able to see some voltage. Now unfortunately I couldn't throw this stuff on this screen. So you may have to just believe what I see here. Even if you cannot see, you have to just make it believe. Okay. So maybe the people from the very front, they will be able to verify. Okay. So I'll just put it here. Okay. Let's see. Is it visible? Okay. So if I turn on the power, I expect that this guy would accumulate charges, and we're supposed to see some reading on this multimeter. So if you guys in the front, if you can volunteer me a little bit, and just read what you see on the screen, and just relay it out to your peers in the back. Okay? So right now you should see some values. What are those values? You can come from. I mean, you don't have to see.
Let's it forward a little
Yeah, you
bit.
can come forward. You can actually help me out.
All right.
Thank you so much for your volunteer. Today we are going to lose one body. Okay. Thank you so much. What's the name?
Isaac.
Isaac. Okay. Isaac, let's do this. And so what we're seeing here is, can you please relay it to the people in the back? What do you see here?
It's negative 41.
Not volt. See, rubber.
Oh, no.
It's millivolt. Okay. So it's millivolt. And once we turn it on, we're going to see that how much volt it is. Right now it's millivolt. That means it's a very, very low amount of voltage.
Is this being measured in direct current voltage?
So we'll see.
Okay.
We'll see both.
I gotcha.
So let us turn on and see how much reading do we see.
45 volts.
45 volts. Okay. So previously it was millivolt, like 1,000 times smaller than 1 volt. And now it is 45 volts. And I think it's going more or less 40 volts, something like that, right? It's fluctuating a little bit because this is not the very best stabilizer, but we are getting some voltage, right? Okay. So now the bad part. Can you stop this guy and put this cap on top of this guy? Yeah, very carefully. We should slide it. Did you feel anything? No. You're dead on. Alright. So, as I said, that if you use another metal on top of it, then this guy is gonna have the same voltage that the other metal guy had at the bottom. So both of these guys would have the same voltage. So we're going to test this thing one more time. And if what is said is true, then we should also see the same 40 volt voltage again on the multimeter. What do you see here?
42 volts.
It's 42 volts. So this means the voltage and all of these metals are same. Okay, so this is one point that you should all remember, that if it's all metal, then everywhere on that metal we should have the same voltage. Okay, everywhere on that metal we should have same voltage. All right. Now let's go to another case. So we have another piece of metal, it's a metal ball, and so we are going to do the following. We will bring this metal ball close to this other metal guy. Okay? So if I do that, what do you expect? So we know that it accumulates charges, right? That's why we see some voltage. We see 40 volt voltage. So if we bring the other metal guy, this metal guy has no charges. But if I bring this thing very close to each other, then these charges are going to jump over to the other metal guy. And because of this jumping, we are supposed to see some sparks. We have also seen this kind of spark. Do you remember that which machine did we use? It's called Wimshur's machine. Right? If we bring those two metal balls very close to each other, we see some sparks. So we're going to see the same effect here. So let's go ahead and push the button. Right now there is nothing, right? Because it's too far away. Let us bring it close to each other and see what happens. So question to you guys. What effect do you see? What effect do you see when I bring this other guy closer to this metal ball?
The ringtone goes off.
Thank you, Isaac. But I mean, it will help also, okay? From time to time. So if I bring them closer to each other, you can see that spark goes on, but something changes. What changes do you see?
The how often that
How often the spark happens, right? The frequency increases. So the charge jumps up more frequently if I bring them closer, right? And in fact, if you can count that how many charges are jumping off, how frequently they are, they will exactly gonna be proportional to 1 over r squared. Okay? Yes.
So if you leave it close to each other for long enough, will the discharges stop because the charges will be equal?
Right, good question. So we'll see all these things, okay? Thank you for asking this question. Yes, go ahead.
So when you were first bringing it closer to it, you could actually see it discharge, like it was the blue spark, but then the closer you got it, we couldn't see that anymore. Why is that?
Yeah, that's also a very good question. So before I answer that question, what is your guess? That's also a very good observation. That when I put them very far away from each other, I could see some charges, but those charges were very infrequent, right? And also they made a very loud noise. Once I bring them closer, the frequency increases, but also it becomes very difficult to visualize, right? That's the question. So we will answer all these questions. It's a very good question, and I'm happy that you are paying special attention to that. So let me ask one more question. We already have two questions, right? Let me ask one more question. What if I bring it so close that I actually touch this other guy? What will happen? In same voltage? They will be the same voltage. So previously we measured it. Give me 1 second, please. Yeah. I know that people are interested. Thank you for asking this question, but give me some moment. Okay? I'm gonna talk it into a question. So we measured that this guy had 40 volt voltage. If I bring the other guy and touch it, then I expect that this guy is also going to have the same voltage. This is exactly what we learned a moment ago. That if we bring all metal together, as long as they are in close contact, they will have the same voltage. But in order to have the same voltage, you see, V equal to KQ over R. So Q must be non-zero in order to have the same voltage, right? So previously it has no charge. If I bring them close, then Q is going to increase for this guy, right? And Q is going to increase unless the voltage for this guy and this guy become same, correct? Okay. So let's look at the other equations also. It says that V equal to KQ over R. R is actually the distance from your charge, right? Now, this guy has one particular, we can approximate it as a sphere. Okay? It's not exactly a very good sphere, but an approximation is good enough. This is also a sphere. So these two guys have totally two different radius of the diameter. That means, although both of these guys will have the same voltage, and we are going to measure it, do you think that both of these guys will have the same charge? And how do you know that? Because it says that V is proportional to Q over R. That means the guy which has the lower radius would have the lower charge, right? So they have the same voltage, but they won't have the same charge, correct? So this is very important to know. All right, so let me go back and answer the question that you guys raised. So what if I bring them very close to each other, then I will see the sparks, but this time the sparks become very frequent also. It becomes very difficult to visualize. And why? Simply because of our sense of vision. It has some certain amount of lag, time lag. Do you know what kind of time lag we have? Like if I throw you something on before your eyes take some time to really understand that what it is. And that time is approximately 0.1 second. Okay? So if I quickly change the picture in front of you, your eyes won't really be able to understand that whether there is a change or not. So when we bring all these things very close to each other, because of the increase of frequency, you really do not be able to understand that whether the charges are really sparking or not. It may look like to you that it's all continuous. It's all continuous, okay? And that's why the frequency increases and the sound also becomes continuous. So let's try one more time. Okay. So with that, Isaac, would you mind to help a little bit? So if you can take these two guys, and we're going to probe the voltage difference between this and that. And you're going to say out loud that what do you see? What do you see now?
0.
0? Millivolt?
Yeah, it's like it's, there's 100 millivolts.
Okay. Let's put both of these together. What do you see?
About 0.
I mean, it should be millivolt, right?
Yeah, well, that's why it's fluctuating. About like 10 millivolts.
10 millivolts. So this means it's actually very low voltage difference. Almost we can say that these two voltages were pretty much same. What if I take one of these guys, I attach it to the ground, okay, and I'm going to take the other guy, and do not touch it. If I take it a little bit away from the Van de Graaff generator, would I be able to see any voltage? What does your common sense say? Let me ask this question one more time. This is going to generate charges. We know that if it is charged, then we'll have some electric field. Those electric field would be radially outwards, right? So it's not that the electric field is only on the top of the surface. Electric field is all over the place. It's just that the further you go, the lesser the strength of the electric field is, right? So if I take this probe and try to measure the voltage, not here, but somewhere here, should I be able to see some value or not? Let's see. So Isaac, one more time. Sorry, I'll keep it straight. Do you see any voltage?
Yeah.
What voltage is it?
5 volts.
Just 5 volts? So it's already giving you 5 volts. Okay? And what if I just bring it closer? If you can come a little bit closer and help them to see.
Is that 22?
It's already 22 volts. What is it?
28?
28. Okay. How about
37?
Wow, it's going increasing. What is it now?
40?
40.
Still 40?
So I cannot go any further closer. It's already touching each other. So you see that the electric field that we talked about so far in this class, these are not imaginary, these are real. And that's why when even we do not touch these guys, each other, when we put them far away, still it registers some amount of voltage, right? So you understand that in order to register voltage, you really do not need to touch two stuff to each other. You can stay a little bit away. For instance, let's say this is your Van de Graaff generator, this is the sphere. If you take your voltage probe, put it somewhere here, you will be able to register some voltage. Okay? And how much voltage it is, that's the electromagnetic field. Q over R multiplied by K. Alright, so we are sure that electric field exists. Okay? So far probably you didn't know, you only did the math. Now you know the electric field exists and electric field reduces as you go away from the source. Alright. So let me ask the following question. What if I could go even further inside of this sphere? So inside the sphere is hollow. Okay. So I say that if you take these voltage probe, bring them closer, you are going to see an increase of voltage according to Q over R. R reduces, that means voltage is going to increase. But we cannot go any further inside. What if we try to go from the interior of it? What does your common sense say? Go ahead.
Maybe more.
Maybe more. That's a good idea. Why do you think that it could be even more voltage?
I think the field would bounce around, but I don't know if that.
Yes, go ahead.
I think it would stay the same as the maximum voltage we'd read on the outside.
Okay, so you think the voltage is the same?
Yeah.
What is the justification?
Since the net field inside of it, if you think of the divergence, it would be zero inside of a volume that doesn't enclose a charge. So the potential would just be constant inside of the sphere.
Okay, all right, that's a good idea. What else? Any other thought? So we have taken two different opinions. One opinion says that the voltage is gonna go up even further, and I think the idea is that since the radius is inversely proportional to the voltage, if I reduce the radius, then of course the voltage is gonna go up even further. That's a good guess. The other guess was that maybe the voltage would remain same because the electric field might not change inside. So we'll see. Okay. So one possible way of testing this idea is the following. So let me take this out. So we are going to do the following. We will keep this upside down. So in that way, now we'll be able to see what happens if I take this probe even further inside into this piece of sphere. Isaac, one more time please.
Okay.
Who's going to hold the bolt?
I think the body holds.
Hopefully.
All right. So previously we have seen that if we take this probe, bring them very close to each other, we are going to see a rise of voltage. Do you still see that? Okay. What if it is now? It's almost 40. Okay. So now we have a chance to go inside and let us see who wins. Okay. Actually, it's nothing about win or lose. It's all about this current. So nobody wins, nobody loses. What do you see?
40.
So I'm almost at the center. 40.
Negative.
So I'm going to move around this guy. Do you see any change? No change. Can that be here? That's okay. Now reducing. So this means if I take this guy, thank you, Isaac. So this means if I take this guy and put it inside, we don't see any change in voltage. Okay? This guy says V is equal to KQ over R. It says that if radius reduces, the voltage is going to go up. That means something is not quite right about these equations. Or maybe there is even more in the story that we have not yet learned about. Okay? So these guys, this V is KQ over R, cannot explain that why voltage increases, doesn't increase anymore if I go inside. So what is going on here? Let's try to understand. To understand the phenomena, let me draw a diagram. Let us say that we have a sphere So I'm going to draw three identical spheres, and we should try to draw the electric field for these three spheres. Okay? So let's say that this sphere has some positive charge on top of it. Okay? And we know that if it is a sphere, then the electric field at the outside would be radial, right? All the electric field would be radially outward from the sphere. the electric field inside? I know that we have not discussed about this, but what does your common sense say? If I draw, let me draw 3 different electric field distributions at the interior of this sphere, and you guys will be helping me to guess that which one might be the correct electric field distribution. Okay? So I'm drawing one of the possibilities is probably this. So this is one possibility. Maybe this is the other possibility. Maybe this is the other possibility. We don't know. Okay? We're just trying to find out that which one could be the right electric field distributions. So this is case 1, this is case 2, and this is case 3. What do you think? Which possibility seems more intuitive?
If this were a truly closed hollow sphere, probably 3.
Probably
But
3.
since it is an open surface, or
Don't worry about the open surface too much.
Okay.
Just consider it's a closed surface, okay?
Okay.
Don't worry about too much.
Fair.
And I will tell that why that small opening doesn't matter too much. For now, just imagine this is a very nice hollow sphere. Which one will get your vote? 1, 2, or 3? 3. Okay, because the 3 seems more symmetric, right? All right. So if 3 is the most reasonable distribution of electric field, we knew from Poisson's law that the divergence of electric field is equal to the charge density divided by epsilon. Okay? So it says, guys, are you following? Okay. So please pay special attention because those will be excellent questions, items for the exams. And I'm afraid that those are not covered in the book. So Poisson's law says that if there is any charge, then on that position of the charge, there must be a divergence of electric field. Okay? On any charge, if there is any charge, we must have a divergence of electric field on that point. So, and we know that how to know the divergence exists or not. Divergence can be thought of as a water flow. If you think that the electric field looks like there is a sink of water, or electric field looks like there is a source of water, it means that divergence is non-zero, right? So, what is the divergence for these guys? If I draw a box here, right in the center, what do you think the divergence would be? Would it be positive, negative, or 0?
Negative.
The divergence would be negative, right? So everyone understands that it is not 0. It cannot be 0 because it looks like it's a sink. It's a sink of water. All the water is dropping through this hole. Now tell me this. This is a hollow sphere, right? If a charge exists, the charge can only exist on the surface. It cannot exist inside it because there is nothing inside that can hold the charge. So if the charge doesn't exist, the Poisson's law says the divergence of electric field is 0. If there is no charge, there cannot be any divergence of field. Okay? You follow? So there are 2 possible ways by which we can say the divergence is 0. One is this guy. If I draw a box here, do you see that what is the divergence? What would be the divergence? Just think about it, whether it's a source or sink. 0. It's not a source, it's not a sink. So maybe if Poisson's law is true, then this is one of the possibilities, because this is how we can get zero divergence. However, you just agreed that this is very impossible situation. Why? Because it has to be symmetric. Look at that. It is due in such a way so that one of the surface is having an arrow going outward from it, and the other surface having an arrow coming interior to it. So it's an impossible situation. It cannot be asymmetric. So this is why this term, despite we see that the divergence of electric field is going to be zero, it's not a possibility. Electric field cannot look like asymmetric. It's a symmetric situation. So this is crossed out, despite divergence of electric field is zero. Okay? The other possibility was this. You say that this looks more symmetric. But I say that Poisson's law is going to contradict with these situations, because it says, despite it looks symmetric, the divergence of electric field is non-zero. But you know that there is no such rho, no such charge density interior to it. So this is also an impossible situation. The Poisson's law cancels out these situations. So the only other possibility remains is the following, that there is no electric field. Look at that. If electric field itself is zero, then divergence of electric field is also zero. Okay? Divergence means dx plus dy plus dez. So if I tell Ex, Ey, and Ez all to be zero, then the divergence of electric field is also going to be zero. Okay? And if divergence of electric field is going to be zero, then it matches with the Poisson's equation. It says that indeed if there is no charge, then this guy is going to be zero. So in fact, neither 1, nor 2, nor 3, none of them are true. Do you follow? Why I say that this 3 is not true? This is not true because if this were true, then we are going to violate Poisson's law. It says that divergence must be non-zero. So the only possibility is that we don't have any electric field interior to it. Okay? All the electric fields would be actually outside. All the electric fields will be outside. Okay? So that's something that might not be very obvious from common sense, but this is how it is. Okay? If you take a sphere, if you take a hollow sphere, there will be no electric field interior to that sphere. Okay? This is also true if it is not a sphere. Let's say that we are talking about a rectangle. Alright? Let's say this rectangle is made of metal. If it is an enclosed surface, the electric field interior to this metal guy will be zero. If you give some charge on top of it, all the electric field would be outside. Okay? So let's say that you are stuck in a lift, and somehow the lift is electrocuted. So the electric field will be inside or outside. Outside. There won't be any electric field interior to the lift as long as the entire structure is made of steel or a metal. So this means despite this lift might get electrocuted, you are completely safe inside. Safe, alive, and breathing and kicking. Don't try to go outside, okay? Then you'll have a problem. Okay? You can even touch the wall of the lift, even if it is electrocuted, as long as it is interior. Okay? You can touch that wall of the lift. You'll be completely safe. You will be completely safe. Okay? Let me show you that what happens if you really are stuck in a lift, and whether you can get some effect or not. So So we're going to do the following. We have some small metal balls made of aluminum foil, and we'll again create some charges on this guy, and we are going to bring those small metal balls close to this guy. Okay? So if these are charged, fully charged, these metal balls are neutral. If I bring them closer, what would happen? Let's say I bring them closer. Initially it is neutral. If I bring them closer, what do you expect to see? Discharge, right? And it will discharge, that means it is going to accumulate some charge, right? And it will discharge until the voltage of this guy and the voltage of this guy becomes equal, right? That's what we see. And as long as the voltage is not equal, we're going to see a charge exchange between the bigger surface, bigger sphere, and the smaller sphere, right? And how much charge is really needed to get up to the same 40 volt voltage for this guy? Not a lot, right? This guy is very small, so the radius of this guy is very small. That's why to get up to the same amount of voltage, we need just a little bit of charge. The Q has to be very small. Okay? So if you take two guys, one is a larger sphere and one is a smaller sphere, if you bring them closer, both of them eventually will get 40 volt voltage, so the same voltage. But this guy will have a higher charge. This guy will have a lower charge. Okay, remember? Because it's the size. Okay? The smaller the radius, the smaller the size. Alright, so you know that if I bring this closer, we'll have the sparks. Let's see whether we can go a little bit further. Once it has sparks, then it will have some charges, right? So let's say that we have some negative charges on this sphere. If I bring this other guy closer to it, it's also going to have some negative charges, right? But we will also know another thing, that two charges, if they are of the same sign, then they are going to repel each other, right? So if I bring this guy close to each other and touch it, then they will going to exchange the charge, and they are going to have the same charge. If they have the same charge, do we expect them to stick on this surface? Or it will go out? It will repel, right? So let's see, if I take this guy, and put it on top of it, you say that all of these guys is going to have the same charge, but if they have the same charge, they are going to repel each other. So eventually we are going to see that these guys go out of each other, right? Go as far away as possible from each other, right? So we should see some jumping and bumping. So let us see if this is true. Right? They're moving up and down. And all right? So now we know that why they jump. They jump because they got the same charge, and same charge repel each other. So this is what we have not seen here. We have not seen these guys jumping around because of what? Man, it's too heavy. It's just too heavy, and that's why people took this other aluminum foil just to make sure that these have very little amount of mass, okay, so that we don't interfere with gravity. That's the only reason why we tried with this small aluminum foil. Alright, so let me try one more thing. This is a piece of metal. It's a piece of metal? Really? Oh, sure. It's not. What is it? It's just paper. Okay. It's a piece of paper. Not bad.
So you can say whatever way you want.
I can't see it from here.
Yeah, I'm sorry guys. I expected that we could throw stuffs on the board, but
Just a piece of solid plutonium.
see, that's a very good guess. Okay, so I bring it closer. Okay, maybe I can bring it.
There we go.
So yeah, you can go and watch the YouTube, then you'll see that what kind of plutonium it is. So this is a piece of paper. Okay. Now before I put it into experiment, my question to you guys that what's going to happen? What does your common sense say? We know that if we put aluminum foil, which is metal, close to that guy, then both of this aluminum foil have the same voltage as the larger sphere, and they have the same charge, and they're going to repel each other, and we're going to see jumping and bumping. But if it is a dielectric, what will happen? Nothing. No, but that's not a bad
Base
idea.
it on the
Maybe
ink.
there is a reason for that.
If we base it on the ink example you gave us, it'll get partially charged.
Good. Go ahead.
And then if it gets partially charged, then it'll behave in some way. I don't know which way, I can't guess, but I know
That's a good idea. So,
If we were to stand up with if it's partially charged, the negative charge would be attracted. You should stand up, I guess, perpendicular to the surface of the ball.
okay. What else? This is a very nice thought. In fact, all of these are very nice thought. Okay. Even when you say that it can do nothing, probably I think that's not a bad idea, because this is not a conductor. So maybe it's not going to attract any charges. Okay. So I'm not going to discard any of these ideas. These are very good ideas. Thank you. So, and one of the ideas was that because it's a dielectric, so maybe if I put them in an electric field, it will have partial charge on one side and partial negative charge on the other side, right? So, if I take this, if I put this piece of paper on an electric field, then probably one side of it would get partially positive and the other side of it would get partially negative. Okay? So if one is partially positive and one is partially negative, then the negative guy, let's say that this bigger sphere has a negative charge, and this guy would have some positive charge at one side, some negative charge on the other side. Then the positive guy would come closer to the negative guy, right? And the negative and the negative charge, it go farther away from the positive guy, right? So let us see whether this is true. This time, I'm going to just put it here. So we are talking about the following scenario. We say that we have a larger sphere. This sphere might be having some negative charge. If this is true, then this guy this small piece of paper, it might have some positive charge on one side and some negative charge on the other side. Some positive charge and some negative charge on the other side, okay? Now, the positive charge will try to be remaining as close as possible to this negative guy, bigger negative sphere. The negative charge will try to be as far away from this negative big sphere. So eventually, we expect that this guy will change its orientation. Maybe this is a better orientation. This is negative charge, and this is positive charge. Right? So let us see. Well, I have not tested it previously, so this should be fine. You fall down?
Yeah.
Let me put it in this box. It doesn't. Oh, it does. Oh yeah, it's my cue. Yeah. Thank you for standing up. So this guy requires a standing ovation, but it's okay if you keep sitting and clapping. So physics wins, right? Physics is true. Indeed, this guy stood up because this guy wanted to have such a situation so that the positive charge is the closest possible nearest neighbor of this bigger sphere, and the negative charge is at the farthest possible orientations, right? So you see that the dielectric and the metal have very different behaviors. If it were a metal, you need to take the same charge and just go away. But if it were a dielectric, you need to be partially positive and partially negative, and that's why it stood up. Okay? Does anyone have any questions so far? Okay. Good. So I think you guys raised a few questions regarding when I started this experiment. I forgot that whether I answered all of these questions. Did I leave any questions unanswered? No? Okay. Yeah. So tell me the following. We know that if we put this guy like this and put some aluminum ball on top of it, this aluminum ball is going to get the same charge and they're going to repel each other. They're going to fly around, right? Now you have to answer this. So answer this very carefully. If I put it upside down and put this guy interior, what will happen? Once I power the button.
Nobody on the side, so
Yes.
nothing should happen.
Because we discussed that if there were field interior to this, then Poisson's law is going to be violated. Poisson's law says that if there is no charge interior to it, there will be no electric field. Okay? All the electric field is outside because the charges are on the surface. So you go outside of the surface, you get electric field. That's why you will see some jumping. But interior to this sphere, you don't see any jumping. So let us see if this is true. Yeah, I said, can you verify if they are jumping?
Wait after.
You're not jumping.
And you have seen that. So you know, I know that if you are really stuck in a lift which is made of metals, even if it is electrocuted, you are completely safe inside. Completely safe. Isn't it amazing? Just try to get out of it and see what happens. So, I think we talked a lot today. Maybe you guys need some rest. So we will bring this stuff again one more time and try to understand some other interesting stuff, like what is capacitance, what is charge, what is current, etc. Okay. Today we can dismiss the class. So, but please make sure that you really take these ideas, concepts at your home, discuss with your peers. Try to imagine even more scenarios that we have not discussed. For instance, we discussed about the sphere, we discussed about the lift. What could be the other possible scenarios? Let's think about also this way. I say all the time that it's a sphere, but it's not a sphere, right? It's an up sphere. Why an up sphere could also give us the right answer, despite it's not symmetric completely. Just think about it and try to find some answer. All right, and be very watchful that those will be excellent items to ask questions in the exam. Thank you so much.
Thank you.